Hello, everyone. Welcome to Science on Tap, Minocqua. Thanks for coming. My name is Carol Warden. I work at the UW Trout Lake Station up on Trout Lake, just about 10 miles up the road. Science on Tap is an example of the Wisconsin idea, an idea conceived in 1905 that the boundaries of the university are the boundaries of the state. At Science on Tap, you won't get a lecture, but rather you'll have an opportunity to learn and ask questions about different topics. And I'll remind you that you can watch our Science on Tap in 4 different ways. You can watch right here at the brewery, right now, like we are. Live streaming at the Minocqua Public Library. And there's live video streaming with an internet connection as well. So from your own laptop at home, you can watch as well. And then also, you can watch an event later and go to Science on Tap Minocqua and watch archived videos. And we also have an 8 to 10 minute short for each Science on Tap that we do as well. I'd also like to thank our partners, the Minocqua Public Library, the Lakeland Badger Chapter of the Wisconsin Alumni Association, UW Trout Lake Station, UW Kemp Natural Resources Station, and the Minocqua Brewing Company. So, before we get to tonight, just a quick reminder that our next Science on Tap will be November 6th, and our speaker will be Dave McFarland of the Wisconsin DNR, and he will be talking about wildlife research in the Northwoods. So tonight we have Dr. Maggie Turnbull. Maggie is an astrobiologist whose expertise is in identifying planetary systems that are capable of supporting life as we know it. One of her ongoing passions is in understanding our nearest neighboring stars in detail, especially with regard to whether these stars might have habitable planets orbiting them, and what kind of technology it would take to discover and explore these planets. She developed a catalog of habitable stellar systems for use in the search for extraterrestrial intelligence, also known as SETI, and she has studied the spectrum of the Earth to identify the telltale signature signs of life on planets. She's currently leading the science team for NASA's W-FIRST mission, which maybe we'll hear more about later. It's slated to launch in 2025, and in 2019, she was appointed to NASA's Starshade Technology Working Group. W-FIRST will be the first mission to take pictures of planetary systems orbiting the nearest sun-like stars, and the first mission with the hope of determining the atmospheric composition of surface characteristics of those planets. All right, we have an anecdote of Maggie's. I was talking with her on the phone earlier this week and got quite a funny story, a few funny stories actually, and this was one of my favorites. So, on one of Maggie's visits to the 61-inch telescope on Mount Lemmon, north of Tucson, she had the good fortune of bringing a special visitor with her. It quickly became apparent that it was challenging for this visitor to move about the buildings and from building to building with the arbitrary security codes that they needed to go in and out of the doors. So to circumvent triggering every alarm known to man, trying to remember these arbitrary security codes, they left one door open just a hair so the visitor wouldn't have to memorize or chance punching in the wrong code. In the meantime, somehow a squirrel managed its way into the building, quickly found its way down to the furnace room, starting its tail on fire, and there was Maggie and her special guest chasing around a smoking squirrel, trying to make sure that the alarms wouldn't go off and also keeping the 61-inch telescope secure. So, here is your trivia question. Who was this special visitor? Was it a friend who happened to specialize in small mammal trapping? Her mother? Or Jodie Foster after her role in Contact? It was her mother. Thanks again, Dr. Maggie Turnbull.
Thanks. Yeah, I had a lot of adventures at that telescope. The 61-inch telescope is one of the few big facilities left in the world that graduate students at the University of Arizona were allowed to learn how to use and then run by themselves for days or even weeks at a time while we were gathering data for our research. And I spent a lot of nights by myself on that mountain, and that was not the only mishap the only interesting story that I took away from that telescope. I should write a little book, I think, sometime. But as Carol was mentioning, my passion my scientific passion is in trying to understand whether there are other life forms in the universe besides the ones that we find on Earth. And right now, I'm having my first experience of being involved in a NASA flight mission from the ground up. So the W1st mission entered phase A in 2016, and now we have just actually, at the end of this year, we'll be entering phase C. So we'll be at the point where phase C is when you start cutting metal for the final flight hardware, and I'm leading a science team to, our responsibility is basically to work with the engineers and help to define what the specifications are for this camera that will take the first pictures of planetary systems, whole planetary systems, orbiting stars that are near to the sun. These are all stars that you could see with your naked eye. If you walk outside, they're bright, they're nearby, they're similar to our own. Some of them we know do have planets around them. We know for sure because we've been monitoring them for decades in their motions, the wobble on the star, just the gravitational influence that the planet has on the star. Even though the planet is very small compared to the star, there's a little bit of gravitational influence that causes the star, which is the only thing we can see is the star, to be moving apparently like closer to us and farther away. Like in that motion back and forth, we can detect that and deduce that there are planets in orbit around it. So these are so-called known radial velocity planets, and we hope to take pictures of them. But there could be more planets in the system that we don't know about because they're below our detection threshold when in detecting that motion. And those might pop up in these images, so there's some discovery space there in addition to the ones that we know about. But for this very first mission to fly a camera to do this, it's nice to have some known targets that, like, if you don't see them, there's something weird going. There's a problem, but we're sure that they're there, and so we're designing a camera to be able to see them. And my job is to, first of all, work with the engineers to help them build the right camera so that we actually can see them and learn something interesting about these planets. And then also to work with the whole rest of the scientific community, which we've never flown a camera like this before. We've never had pictures like this to work with before. I mean, that's not entirely true. We have there's definitely some heritage for this, but teaching especially the younger people in the field who want to go into this and they want to be involved in big missions to take really detailed pictures of lots of planetary systems and find the ones that have life on them. For now, we're just going after the ones that we know about, which are big. They're like Jupiter-sized planets. And it's a big stretch for us to hope that we might find a planet that's more like ours with this particular camera. I mean, it's the first one. We've got to start somewhere. And but this new generation of scientists coming into the picture wants to be involved in bigger missions that will actually be able to find planets that are like our own. And so part of my job in supporting this mission is to work with the wider community of early career people and more mid-career and senior people too who just want to know how to do this, to fold in all the data, all the observations that we have, whether it's radial velocity measurements going back decades or other kinds of measurements with these images in order to really pin down and learn as much as we possibly can about these planets. Because this kind of experiment is just incredibly difficult. It's the most high contrast photography you'll ever do. Taking a picture of a tiny little planet right next to a blazing star 10 or 20 light years away. And the contrast ratio there, you know, the planet is maybe 1/10 billionth as bright as the star, and it's separated from the star by maybe an arc second, which is a 60th of a minute, which is a 60th of a degree on the sky. So it's a really hard imaging problem, and we need tricky technology to be able to do it. So Carol mentioned the star shade that I'm also working on, which is a possibility for this mission. So we're just flying a camera that is going to have an internal mechanism that will block out the light of the star so that you can see the light of the planets. But what we're hoping to also do, and the mission is baselined to be star shade ready, which means that if NASA should get approval from Congress in the early 2020s to fly a rendezvous probe, Starshade, that will go to where the telescope is and align with the telescope as an external shield, basically, to align with the star, block out the light of the star, and see planets. Then now all of a sudden this mission becomes much more capable, and we would be able to see Earth-like planets around these sun-like stars, which is kind of the holy grail. And again, it would just be the first step in that, because ideally we would do this for tens or hundreds of stars in order to have a real hope of finding something super interesting. But this would be the first step in demonstrating that we can do this. And with a star shade is, you could think of it as a giant sheet of plastic shaped kind of like a sunflower. It's got a really specific shape that it has to have in order to block out that starlight and basically just aim it away from the telescope so that it casts a really dark shadow over the telescope of starlight, a shadow in that starlight. And then you can just see, you can make out the little planets just off axis to the side of that shadow. And actually, star shades are great. They're super dangerous. They're like giant Chinese stars. Like, they have metal edges that are filed down to a knife edge, and everything has to be really fine and really like to microns in the shaping of it and the sharpness of it. So in the Starshade lab, it's like one of the more dangerous places that I go. And they'll have just one petal of a starshade, and it's got this very perfectly calculated shape, and then a tip going like feet beyond that you can barely see, and it's all like sharp, knife edge sharp, and you gotta be careful you don't snag your sweater on it or something. But that's a possibility for this mission as well. And then we actually are talking about being able to find Earth-like planets around some of these stars if they're there. But I was hoping that you all would join me in to sort of like just prepare right now to expand our minds a little bit in a quick visual exercise, a quick mental exercise, just to lay the groundwork for what we're starting here. Because this topic is so vast and there's so many different directions we could go. But I wanted to just like get some quick personal experience and just a lay of the land of what we're talking about. So if you join me, I invite you to close your eyes for a minute. Carol has said she would stand sentry to make sure nothing suspicious happens while our eyes are closed. But if you just close your eyes with me for a minute, and we're going to start with just a simple recognition of where we are right now in this room. I mean, I'm so grateful to be here, and I think about all the people and all the things that had to come together in order for us to be here together and discussing this incredibly vast topic, and just the whole history, actually, of humanity, even, and how far we've come to even be considering that we're actually going into space and we're actually discovering the rest of the universe firsthand. But so I'm gonna make it real personal to start. So, breathing in, I'm aware of sitting in this room with all of these other people who came here tonight through the rain and are interested in knowing what's going on out there. And breathing out, I'm aware of myself being here and being a part of this and these precious, quickly passing moments together. Breathing in, I'm aware of the city that we're in and the state of Wisconsin and the Wisconsin idea that is making it possible for us to be together right now and contemplate these things. Breathing out, I smile at that idea. I think it's fantastic that we're able to be together. Then just contemplate the bigger picture of the earth and beyond Wisconsin. Right now it's nighttime. The sun is below our horizon. It's overcast, but the earth itself is in our part of the world turning into night. The city lights are glowing. People are getting ready to settle in for the night all over. And the earth is slowly turning in the vastness of the cosmos. The sun is shining on the earth, and the moon is orbiting the earth, and we can expand our awareness beyond the Earth-Moon system to include the other planets in the solar system, Venus and Mercury, going toward the sun, and then going away from the sun. We'll move past Mars, the red planet, and through the main belt of asteroids out to Jupiter and all of its incredibly interesting system of moons, some of which may or may not actually be habitable to life as we know it, and moving beyond Jupiter out to Saturn, its incredible system of rings and moons. Again, very unique, possibly that ring system, possibly only very transient and not very long lasting, but it's here with us now. Moving beyond Saturn to Uranus and Neptune, these sort of large, dark, mysterious blue planets that are in between the size of the Earth and Saturn, that they're out there in the depths of space. And then beyond Neptune, another belt of objects that are Pluto-sized. Pluto is one of them, and there are many more, many that we haven't discovered yet, some that are bigger than Pluto, many of which have, it's actually more than one object orbiting together, like binary planets. And then beyond all of that, moving into the Oort cloud of comets, a giant spherical cloud of comets that spend tens of thousands of years far away and then occasionally swoop in, passing close to the sun and back out again. And as they come close, their ices start to evaporate and they grow these really long tails and swoop through past the sun and back out again. Some of them every few decades they come back, and some of them only once every tens of thousands of years, but a giant reservoir of water in our solar system. And then if we imagine beyond that to the nearest star system is different from ours. The brightest star in it is a star very similar to our sun, but it has a companion star that's a little bit fainter and sort of an orange star. So the two of them orbit together around each other. And then they have a third star around them, Proxima Centauri, very faint little red star that is representative actually of what most of the stars in the whole galaxy are like, is these faint little red guys. So we can just then from there maybe just expand our awareness even bigger to include the whole Milky Way galaxy of stars, about 400 billion of them. It doesn't matter if you can hold that number in your consciousness or not. It's a lot. It's a lot of stars in the galaxy. And Milky Way galaxy has spiral arms. It's kind of flat like a pancake, but it has these spiral arms and giant clouds of gas and dust in between the spiral arms. The spiral arms are all just stars. Stars, 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 stars. Every star has its own planetary system. These giant clouds of gas and dust are gradually over time coming together and precipitating out new stars, like literally raining out stars as these waves sweep through the whole spiral galaxy. And then going beyond our galaxy and expanding our awareness even larger than that, there's a satellite, small satellite galaxy to our Milky Way galaxy, and beyond that, there's another big spiral galaxy like ours, the Andromeda, our sister galaxy, gradually heading toward us. Eventually, there will be a collision. It'll be interesting. And going beyond that to the local group of galaxies, spiral galaxies like ours, little dwarf spherical galaxies, bigger spherical galaxies. Just use your imagination. There's lots of kinds of galaxies, and they all have lots of stars in them. And then let's just let our awareness expand to the entire visible universe, which contains about as many galaxies as there are stars in our own galaxy. So, 400 billion stars in our galaxy. Our visible universe includes about 400 billion galaxies, each of which contains hundreds of billions of stars, each of which has a planetary system of some sort. And then beyond that, beyond the observable universe, apparently, it just continues on like that forever. Every indication shows that there isn't an edge to our universe is not finite, it's infinite, it's expanding, and on the very vast, going even vaster than all of that, you can appreciate your own mind and the ability of it to contain all of this, and at least imagine it. We're all at different places in what that looks like. Right now, we're sort of all holding different universes in our minds, but nevertheless, it's there, and we're capable of comprehending this and relating to it in a very personal way. So then just landing ourselves sort of back in this room with ourselves, appreciating the vastness of our minds and the things that we can contemplate and relate to in a personal way, and an expression of gratitude. And thank you for joining me in this tonight. And you can open your eyes now. Now that you're asleep. I got nothing else to say.
This mission that you have coming up where you're going to go with the camera to see the stars, how are you choosing those stars with their planets? Are you narrowing it down somehow? I'm sure you are.
Yeah.
It's more likely to see life.
Great question, and actually the most important question that we've been talking about over and over and over and over again for the last few years. We're going to look at the easiest ones. Is basically what it comes down to. Some of these planets are, what we know about them is a rough estimate of how big they are and how close they are to their star, because what the radial velocity data tells us is, one, we can tell how long it takes for the planet to go one time all the way around that star, pulling it back and forth. So we know if it, does it take 1 year or 3 years or what? So that tells us how much of a separation it's going to have from the star. And then we also have an estimate of how massive that planet is. And given that, we can have very, very approximate guesses or somewhat educated guesses at how bright it's going to be and how far away from the star. And we have to dovetail that with the technology that we think we can advance to take those pictures. And if the planet is very close to the star in a very tight orbit going around very fast, it's hopeless. We're not going to be able to take pictures of something that close. But if it's too far away, there's kind of a sweet spot in there where we can cancel out the starlight really effectively, but then further out we start to lose it again. So there's kind of a sweet spot of separation between the planet and star. And then the overall size of the planet, bigger ones are brighter. So if that makes it easier. But we have a list of a couple dozen stars that we hope to be able to get to. But the boots on the ground requirement, as far as NASA is concerned, is that we directly image, we take a picture of at least one of these planets, and that furthermore we get spectral information out, the colors of the planet out, so that we can start to know things about its atmosphere and actually study the planet, besides just know that it's there. So short answer, we're going to do the easiest ones first.
I read back in the 2000s in Discovery that they created a formula to find life on another planet. And it was like da-da-da-da-da-da-da. It was really super long. But when you said spectra, are you looking for particular colors? Because I know green would be one of the rarest colors in the universe that usually is a sign of some sort of wavelength. Is there any merit to that? And can you tell us about that formula if you have some knowledge on that? Because it's been a while since I've heard about that.
Well, I can take a guess at what that formula might be. Does anybody else have a guess at what that formula might be? I'm thinking that, well, you never know, sometimes people know these things, but I'm thinking that what you might have come across is the Drake equation, which is the so-called Drake equation, which Frank Drake is sort of one of the founders of the SETI movement, the Search for Extraterrestrial Intelligence. And he came up with a really super simple equation for estimating how many other intelligent civilizations there are in our galaxy. And it's basically just the number of stars times the number of stars that have planets times the number of planets that are, or I should be saying the fraction. The number of stars times the fraction of stars that have planet times the fraction of planets that are actually habitable to life as we know it, and so on and so on and so on. All these requirements times the fraction of planets that actually develop life times the fraction of lives that actually become intelligent and develop the capability to communicate between the stars and so on. And so beginning with all the stars in the galaxy, you should be able to whittle it down to a number of how many have intelligent civilizations around them that we could talk to. And it turns out, if you go through all of that, given all the uncertainty that we have about each one of those factors, that the number of intelligent civilizations out there is somewhere between, well, other than our own, 0, and like hundreds of millions. So, so we're not sure. But we're trying to hone in. That's why we're taking these pictures and trying to learn about these planets. But the question about the signatures of life, so there's a whole field of study on biosignatures that can be remotely detected. And the Earth right now is actively emitting all kinds of biosignatures, where our planet right now is sending out obviously radio signals from all of our television programs, communications with spacecraft, so on. We're sending out light from our nighttime lighting, just sodium lamps and whatnot. I mean, that is going, it's not a very bright signal, but it is going into space. And furthermore, actually, the Earth has been broadcasting without any help from us signatures of life going back billions of years, including the presence of oxygen in our atmosphere and a vegetation signal. The vegetation plants they look green to our eyes. They're actually very dark at optical wavelengths. So where the sun is emitting most of its light, which is in the optical wavelengths, plants are extremely efficient at absorbing those photons. They are dark. And there's the pigments, the way what do plants do? Photosynthesis. Yeah, the way the pigments absorb that light. There's a couple different pigments, and the way they sort of overlap each other in wavelength space leaves a little bump in the green. So they do reflect some green light, and that's what our eyes are picking up and seeing as this lush, beautiful plant life. But that they're harvesting most of the photons in the optical wavelengths. And meanwhile, in the infrared, not even very far into the infrared, if your eyes were able to detect even just a little bit of infrared light, you would see how bright they are. They are reflecting all of those photons. They are white in the infrared. So we call this the vegetation edge, where if we look at the Earth in optical wavelengths, and then we look at it in the infrared, the continents are dark that have forests on them are dark in the optical, and then they're just glowing in the infrared. That is a clear signal of an organism that is selectively harvesting useful photons from its star. And that's a biotechnology that was invented by plants and billions of years ago. And when it was invented, it destroyed the planet, right? Like it completely contaminated the whole atmosphere with oxygen. Most of life died. Oxygen is not easy to get along with. We have a lot of systems that repair oxidation damage and so on. But that signal has been going out, into our galaxy for the last 2 billion years or so. And that's the sort of thing that we look for. And then the presence of oxygen in our atmosphere is sharply, strongly out of equilibrium with the other gases in our atmosphere. So the simultaneous presence of a strong oxygen signal with methane in the atmosphere, for example. Normally, it's not a very long recombination time for oxygen and methane to come together, liberate CO2, carbon dioxide, and water. I mean, that's what they want to do. Those are highly reactive gases that do not take long to destroy each other. And the fact that there is such a giant oxygen signal in our atmosphere and methane together indicates something is actively producing that. And in our world, that's plants. So, and there's no geological mechanism really that we could easily point to that seems believable, that, just like volcanoes or something. Volcanoes generate lots of CO2, they do generate lots of methane, but that oxygen, that doesn't belong. And so it's an indication of something very suspicious going on. So and that's how we detect all of that, by looking at the different colors of light. And oxygen has a really sharp absorption feature at visible wavelengths. And then another feature we would look for is water. We want to see, water is like the thing that all life on Earth depends on. And water in the infrared, like astronomers can't even look at the stars in the infrared in certain windows of wavelength space in the infrared, because water absorbs all of the light. So starlight coming in, never see it. You have to look between. We have very specific band passes that we put on our telescopes so that we just filter everything out except for those little windows in the infrared where we can actually see the stars. And that's something we could detect on another planet too, that would tell us there's water, we could see that there's oxygen, we could see there's a vegetation or some kind of really interesting surface signature, and all of that comes from looking at the colors coming from the planet.
Question right here.
Oops, sorry. I don't get to choose.
Can you explain how this relates to the Hubble? And then also, that's somewhere up there in space in a stationary platform. Is yours going to go up and park, or is it going to keep going?
Oh, thanks for asking. So I feel like I could just sit here all day talking about these telescopes. Like, there's so many stories that come to mind, but Hubble is a space telescope too. It's in orbit around the Earth in space by itself, alone, not attached to anything. It's just in orbit. It's in what we call low Earth orbit, so it's about 200 miles off the ground. If you can look online to see when it's going to pass overhead. It happens pretty quickly, but if it's the right configuration with maybe at sunset, you can see sunlight reflecting off the solar panels. It's very bright passing through the sky. But it goes around the Earth once every 90 minutes or so. And the W First telescope, turns out, is the same size as the Hubble Space Telescope, exactly, because it turns out there was more than one Hubble telescope built back in the day when Hubble was flown. The National Reconnaissance Office had its own fleet of telescopes that were used not to observe the stars, but they were pointing down. And several years ago, when people were trying to formulate the W First mission, it had been ranked very highly by the national academies, which is the job of the national academies is basically to tell NASA what to do. It's like the peer review system for NASA. And this W First mission to do everything it's going to do was ranked very highly. And so they were trying to figure out, how big should the telescope be, whatever. And then the National Reconnaissance Office, the NRO, the Defense Department, told NASA that it had some leftover telescopes it didn't need anymore from this fleet of Hubbles, basically, that nobody knew about. And at that point, NASA asked all the astronomers in this big meeting, in this big long process, like, well, what should we do with this telescope that we've just been gifted by the National Reconnaissance Office? And a bunch of people showed up at this meeting, and we all had ideas. And the number one idea that emerged was that, well, this W First thing that everybody wants to do, we should make it bigger and use that telescope, because Hubble is a fairly significant, large space telescope. I mean, for considering what we had at our disposal at the time, that was the gift. So now W First, basically a copy of the Hubble, is going to fly, and it's not going to be in low Earth orbit. We've recognized that there are other orbits that are much better for the kind of science, very high precision science that we want to do, especially something like taking pictures of planets orbiting other stars. I mean, you have to have a very dark, quiet, stable environment. So we're going to fly this telescope beyond the orbit of the Earth, and it'll be in orbit outside the orbit of the Earth. Many times the size of the Earth away, but still it'll track with the Earth going around. Basically, it's in orbit around the sun, but the extra gravity from the Earth tugs it just enough that it doesn't move slower. It actually tracks with the Earth all the way around. So it'll be there on our night side, the night side of our planet. Accessible, easy to talk to all the time, but in a very quiet environment. The thing about the Hubble is that it's whipping around the Earth every 90 minutes, and it's passing through things like the magnetic anomaly. Does anybody know what that is? I don't think anybody actually knows what it is, but they have to shut down the whole observatory every time it passes through that because it messes with the instruments. And then not only that, but you're spending half your life on the day side of the planet, and then in the nighttime, and day side, nighttime, day side, night, and the temperature is changing rapidly. That has an impact on your instrumentation and the response of your detectors and so on. And just being there are radiation belts to deal with, all of that. Going away from the Earth to the backside of the planet, further out into the solar system, temperatures very stable, and there's none of this like whipping around the Earth every 90 minutes. You're just stable. So you can start to do this kind of really high precision work that you need to be able to do if you actually want to take pictures of planets orbiting other stars. Does that answer the question?
Question right here.
Yes, the web goes up in '21. How is that, A, going to affect the vision you gave to us with our eyes closed? And B, your mission?
Thank you. Yeah. The James Webb Telescope is a larger telescope that's going to fly first. And it was actually scheduled to launch last year, and then I think it was going to launch this year, and now it's going to launch in '21. So it seems to be James Webb is like the telescope that's going to launch in 3 years, like always, forever. But hopefully it actually will launch in 2021. There was a mishap with the telescope last year during a shake test. There are all these things you have to do. When you get to the point where the whole facility has actually been built and the instruments are all together and you've done all the system testing and everything's talking to everything else and it works, it's together. Then, your precious telescope that you've invested, like, I don't know how many, like hundreds of thousands of human life hours into, has to go into a giant shake tank. And, because it has to survive launch. And so you need to test that and make sure that everything's, well, somebody in the mirror assembly, one of the engineers used a screw that was not to specification. And so in the shake test, those screws, they were not long enough. They didn't thread in all the way as they were supposed to. And they came loose. And so 70 screws came loose in the shake test. And they fell all over inside the observatory, the facility. And then, then they recovered all but like 3 of them. And you can't have 3 pieces loose inside your, how many $billion space telescope, like making it through. That is not an acceptable risk. So the entire thing has to be taken apart and put back together again. And that's going to take 3 years. So that's why James Webb is now launching in 2021 instead of 2018 or whatever it was supposed to be. Anyways, so far, this has not impacted our mission. As of right now, we are still on track. The funding is still, Congress continues to approve the funding we need every year, each year. I mean, each year we have to go to Congress, and this is something where I basically just book my flight, like for every April from now until the mission launches, so that to go to Washington, D.C. and sit down with all of our Wisconsin representatives and say again what we're doing and why this is exciting and new and an important part of NASA's portfolio. But so far, Congress has always backed us up and always said that this is something we want to do. We're going to give you the funding so that you can stay on track, regardless of what's happening with James Webb. Even though every time one of these delays or mishaps happen, we have to go explain it because it probably looks to Congress like we don't know what we're doing, And even though that's a different mission, they want an explanation from us, like, why did this happen? And we have to provide evidence that so far every single thing we're doing is we're not failing any tests, we're passing, we're meeting all of our milestones. Everything is on schedule, it's at cost, it's below volume and weight and all of that stuff. So as of right now, we're okay. But I feel like there was more to that question. Was there anything else in there that I did not address?
If it goes, will we see further?
Oh, yeah. How is James Webb? Okay, the other aspect of that question was how will James Webb change the exercise that we just went through in our minds? And so James Webb is has a number of purposes, including understanding much better how our galaxy is forming new stars and new planetary systems, and how that process actually occurs when you have these giant clouds that are being, as these pressure waves are sweeping through the galaxy and making these beautiful spiral arms. They're pressurizing this gas, and that's literally precipitating out new stars and planetary systems. James Webb is going to be able to really hone in on that whole process and kind of reveal a lot more about how that happens. And then the other thing it's designed to do is to get at this question of dark energy and and the expansion of the Milky Way, or not just of the universe, of the whole universe, and what is driving this expansion to happen. Because not only is the universe expanding, it's expanding at an accelerating rate, faster and faster. What is causing this? And it's unknown. I went to an American Astronomical Society meeting last year. It's the biggest meeting of astronomers every year. There's usually a few thousand people, which is basically all the astronomers. And one of the keynote talks was basically just what's the universe made of. And they had a tally. They had a pie chart of, this made of, this matter that we can see and this matter that we can't see. And basically, at this point, we understand what about 5% of the universe is made of, and 95%, it's like totally, it's dark energy, and we don't know what that is. So most of the energy in the universe it's this mysterious thing that is causing this expansion, this ever-increasing expansion. And that's what James Webb is designed to get at.
More questions? Did we have one over here? Good.
Recently, I attended the climate strike here at Torpy Park, and one of the individual signs was, "There is no planet B." And then I thought, well, wait a second, Jeffrey Bezos, the CEO of Amazon, has a plan to shoot the entire, or almost the entire population of the Earth into O'Neill cylinders in space. And I was wondering if you could comment on that plan.
How many people would like to be shot in a cylinder into space? Like, does that sound like fun? I mean, I guess my comment would be that it's almost like, I don't know whether to laugh or cry because it's like, in some level, I think you have to admit it is a little bit humorous, like that we would be willing to invest so much time and thought and energy into how to blast ourselves into space to get to another planet. And meanwhile, like, we could just take care of the one that we have. And we're designed, like, every single thing, every cell in our body, everything about us is tailor-made to live on Earth. This is our home. And to imagine that we could just pluck ourselves, or any life form for that matter, off of one planet and just put it on another planet, and then it's all going to be okay, it's going to work out, is wrong. I'm telling you. I'm just saying that. I know there are many things I don't understand, but that is one thing that just can't be right. It can't be true. Partly because I have grown a sense of appreciation for the diversity in the universe, that there are no two planets the same. Our solar system has thousands of objects in it. It's a very dynamic place. We have a long-standing history here and relationship of interaction, even with the other bodies in our solar system, that shaped everything about the situation we're in right now today. And it's continuing to change. It's a dynamic, ongoing story. It's not over yet. But meanwhile, all the other planets and planetary systems out there, they're the same thing. They have their own story and their own history and background. And when I am engaged with this search for life on other planets. Um, I'm approaching it from a sense of exploration and discovery and appreciation of the whole big story of what's unfolding in this really interesting universe. But to think about myself going to live on one of those, I'd love to talk to them. I'd like to learn about them. But the problem with having a human body is that you have to keep it alive, and you have to live in an environment that can actually support that. We're evolved to be here, and I think to try to go to another planet, if it's habitable, and especially if it's already inhabited, presents a lot of complications and difficulties, let alone just the journey of getting there and whether you'd want to do that or not, go through that experience. And if you did go through that experience, when you got there, would you then be attached to your ship and not want to get off the ship? Like, I don't know. Human psychology is a kind of complicated thing. So I don't know if that's a very satisfying answer, but that's what kind of comes to me about that whole plan.
These needle cylinders they have artificial gravity. They're giant miles-long cylinders
Hang
that
on.
rotate.
Can you
And
repeat the
every
question?
day will be like
I think I can
greatest
repeat it.
day on Maui.
Yeah. Well, it would be cool to invent that. I don't know. So these O'Neill cylinders are giant things. Has anybody ever read Rendezvous with Rama, by Arthur C. Clarke? Yeah. Actually, that's a great story. But the idea is that you're in this rotating cylinder, and it's giant, and there could be like a whole ocean in there, and it could be like living in Maui, you said, for light source and everything. And far be it from me to begrudge anyone their experience of trying to design something like that and go in it and then travel. And I just personally, I find it to be like humorous, actually, that we would go through all that. And here we are with this incredible planet. I just got done listening to an interview with this was the 50th anniversary of the landing of the astronauts on the moon and walking on the moon. And I just got done listening to a whole series of podcasts with interviews with those astronauts and some of the old recordings of how they felt when they were walking around on the moon. And basically the one thing they couldn't stop talking about was the Earth and looking back at the Earth. And they got in this spaceship, and all they were thinking about up to that point was getting to the moon and moon, spaceship. And then they're up there, and they're just fascinated with the Earth. They just wanted to look at that Earth the whole way there. And then on the moon, when the Earth rose, it was like, wow, look at that. And the comment that I remember is, it was the only thing with color in the entire universe. And this planet is glowing with blues and whites and greens and grays and reds. And a whole rest of the landscape was just dull moon. and I feel like sometimes if we could all have that experience, these kinds of questions might fall by the wayside a little bit. Not that we would want to stop exploring and learning about the rest of the universe, but to just sort of give up the Earth as a lost cause, and we're going to think about Planet B instead and put all our resources into that. I think the ability to actually be taken from our planet and actually look at it from away would cause some of that narrative to subside potentially. I don't know.
Question back here?
So about 5 questions ago, you mentioned Drake's equation. My question is, since you're searching for life on other planets, what is your opinion on the Fermi paradox?
Yeah, so the Fermi paradox, so Drake's equation and the Fermi paradox, these are things that are in the world of searching for extraterrestrial intelligence and communicating with other civilizations, potentially. Those are two really prominent concepts. And Fermi's paradox is, well, Enrico Fermi was actually to my understanding, was actually a proponent of SETI and searching for other civilizations. He thought it must be out there. But he voiced the question of, if it's true that we're not the only ones, and our civilization is very new. I mean, we became capable of communicating at a distance through electromagnetic radiation, through radio waves, like 100 years ago, basically. That's nothing in the grand scheme of things. The planet's 4.5 billion years old. There are other planetary systems out there that are older than this. If there are other civilizations out there, chances are they're going to be more advanced than us because we're new. That's no other not because we're inferior for any reason. We're just new. And so his thought was that if they are out there, chances are they've been around for a very long time, and they've had the opportunity to colonize, by now, the entire galaxy. Like at least one civilization should have, even if it's not that common, should have arisen long enough ago that it would have visited us already, and we should know about it. So if they're out there, where are they? It appeared, and the paradox is, I guess one way to think of the paradox is just that, look, we're here, and it seems like all the building blocks for life as we know it, including intelligent life, are not that rare, where, there's nothing, it's not like the Earth is the only place you find all of these materials and whatnot. And if planets are common around other stars, which we now do think that almost every single star does have its own planetary system, and these, they're basically made out of the same sorts of things, why don't we hear anybody talking? Or how come nobody has come here to tell us about themselves or what's going on? So there have been a number of theories that have come up. My favorite is the zoo hypothesis. I had an abstract of the zoo hypothesis paper from the 70s cut out and on my door at my office door in grad school. It was published in the Astrophysical Journal, and the abstract basically said that in order to address the Fermi paradox, we have come up with a theory called the zoo hypothesis, which is that the Earth has been set aside as a sanctuary or zoo by the other intelligent civilizations out there for remote study. So they don't come here because they're letting us be by ourselves. And so I think about that, and my own theory about how to resolve this paradox is that just having witnessed a NASA mission come together and all the things that can go wrong and all the systems and subsystems and teams and sub-teams and working groups and all this and Congress and everything that has to happen for anything to be launched from the ground into space, just having seen all that, my feeling is that there is only one kind of society that can pull off any kind of space program, let alone an interstellar space. I can't emphasize enough how much harder it is to go from the kind of space program we have, where we're putting things into low Earth orbit that go around every 90 minutes, and compared to going to another star system. That's a whole other ball game. And the only kind of society that can pull off even the littlest bit of a space program is a peaceful society. It has to be, the intelligent life forms have to be able to get along they have to have expendable resources, more than what they need, and they have to get along with each other well enough to actually implement a program this complicated. So that may not happen very often, and B, it may also be the case that traveling between the stars is so difficult. It's such a high bar that to even get to the stage where that is even possible anymore, a civilization may psychologically get to a place where they don't need to do that anymore, where they're learning, they've come to a place where they're not colonizing, they're not taking over, they're not aggressively interfering. And I mean, I'm reminding myself of the Prime Directive right now from Star Trek a little bit. But for an intelligent civilization to get its act together and be that coordinated and that peacefully minded, which I really think is a requirement. Otherwise, you get ego battles that tear it all apart. I've seen it happen many times. You would get to psychologically a place where you don't need to make your presence known. And I think that could actually be real. That could be a real thing where you can explore the universe without interfering with every single thing you see or needing to take it over or needing to live there, but to just let it be.
Question back here.
That was an interesting discussion about the Fermi principle. And when you get together at these seminars with all of your other fellow astronomers, scientists, do they talk about there being a possible Area 51 somewhere that collects these types of unknown intelligence? And what about the people that debase the going to the moon completely?
Yeah, so that's those are two good questions. One is almost kind of opposite ends of the spectrum, really. Like, the belief that we've been visited and the government knows about it and it's hiding it from us, and the belief that we've never done anything, as far as going to the moon, but the government is pretending that they have. So it's kind of like two extreme, or two kind of polar opposite viewpoints. But it's funny because a lot of people seem to have them both. But the thing about Area 51 and have aliens visited us, and I mean that's actually really that's a completely rational thing to ask, right? Like, well, maybe actually they have, but we just don't know that, and that is possible. I mean, again, like, having witnessed how a mission comes together from the ground up and like what it takes in order to pull something like that off. I don't have like insider knowledge as far as like how our Defense Department works or anything like that, but my sense is that it would be really hard to keep a secret like that, especially with all these scientists running around loose who have to tell everybody everything. I mean, our policies, so I still actually I run all my grants through the SETI Institute, the Search for Extraterrestrial Intelligence. That's my home. I did my dissertation with them. I redesigned the target list and decided where we should be pointing the telescope to try to hone in on the star systems that are the most likely to have life, anything close to what we have here. And we had long conversations about this, so like at the radio telescope, listening for signals. And I was there because I was the one who actually knew a lot about each star that we were pointing at. I was there with the engineers and with Jill Tarter, who is kind of the founder of that whole program. And we would talk late into the night about all these different kinds of things. And I can confidently tell you that in all of my conversations with my colleagues, and including the ones of us that want there to be aliens, and we have nothing like that. We have nothing like that we could point to and say, oh yeah, they've definitely visited us, but the government is hiding. I mean, our procedure for SETI, when we go and make these observations and we're listening for signals and we have this huge protocol to make sure that we're not accidentally just detecting our own signals from a microwave or something, which is actually really hard, and it's very complicated process to make sure that to rule out all the false positives. Our plan always, every time we go to the telescope, there is a bottle of champagne in the fridge, and the plan is to crack that open and tell everybody immediately that we have found a signal. There's no, well, we should ask the government if we can tell anybody. There's nothing like that. And scientists have no motivation whatsoever to keep secret anything that they've discovered or learned, especially not when it's something as interesting as aliens. So I cannot say, the government is not hiding anything from us because I don't have inside access to all that, but I can tell you that if any of us knew about it, you would too. But the other question was about the moon and whether it was all a giant hoax. And like I said, I just got done listening to all these interviews with all these astronauts and their experiences of walking on the moon and going to the moon. So if you just listen to that, just the sheer authenticity and the feeling that comes through from describing that experience, it's like it's hard to look it up and be like, oh, this is all fabricated. But aside from that, there are things on the surface of the moon that they left behind that anybody can look at if you have the right tools. For example, they left behind a set of mirrors that are it's an array of corner cubes. Does anybody know what a corner cube is? A corner cube is when you take mirrors, and have you ever been in a bathroom that has like two mirrors at a 90-degree angle to them, and then also like on the countertop or on the ceiling or something? That makes a corner cube. And the thing about a corner cube mirror is that no matter what direction you shine a laser beam at it, it will come back at you to exactly where you are. Like you can move, no matter where you are, that beam will come direct. It bounces off all three surfaces and comes back to you. So there's an array of corner cubes that they left on the moon for the purpose of going home and shining laser at it and knowing it would come right back to them, and using the amount of time it takes for a laser pulse to go from the Earth to the moon and back again to measure how far away the moon is. And that's how we know that the moon is gradually getting farther and farther away from us. And as a result of that, our day length is slowly getting longer. So, if you don't think there's enough time in the day, just wait like a few billion years. It is happening. But so there are things like that they left behind. And people, you don't have to have a really fancy setup. You can have only a moderately fancy setup. Like amateur astronomers, I think, are some of the most accomplished astronomers in the world. They know far more about the sky, the observable, the visible, to your eyes sky and looking at it than a lot of professional astronomers do. And it's sort of that level of technology that you would need in order to make your own observation of some of these things that astronauts left behind on the moon. But I think no matter how I could talk until the cows come home about that, and some people are just not going to believe. Which is okay, because now we're going back again, apparently. We have the lunar gateway that NASA is going to build as an outpost, orbiting lunar outpost that will easily be able to shuttle astronauts to and from the surface of the moon. And that will be a whole new day.
Question here.
Just what is the launch vehicle that you're planning to use for your telescope?
For WFIRST?
Yes.
Oh, great question. It's funny because I was wondering that on the way up here, and then I thought, well, nobody's going to ask that, so I'm not going to look it up. But I think we might be looking at, I almost hate to say this because I know it's going to be recorded, and like one of my colleagues is going to watch it and then tell you like that was totally wrong. But so sorry, but I think we might be looking at a Delta IV Heavy, possibly.
And the telescope itself, to station keep, will it have a propulsion system?
Yeah, so it will have to. What the gentleman is pointing out is that the the orbit that we want to send our telescope to beyond the Earth. It's beyond the Earth, and orbits that are further away from the sun, they are bigger and slower. So things that are further away just move slower through space. And here the Earth is a little bit closer to the sun, moving faster. But the extra gravitational pull is what keeps them from the Earth is what keeps them tracking together. That's a special point in space. And that point in space it's actually a little bit, it's unstable. So the telescope is going to want to fall off that point and either like get lost behind or, it's going to want to fall off that point. It's a very particular, it's actually a big point in space, but it's still, it's like a hill that can be fallen off. So we have to have station keeping, so-called station keeping and local propulsion on the telescope, to maintain. In fact, it's almost like it's in a little orbit around that point, and it will need station keeping. And if there's a star shade that flies and rendezvous with the telescope, it also will have to have its own propulsion.
We have a question right here.
I just was curious if everything goes well in 3 years. What's the time frame that we might start getting some data back?
Yeah, so we are supposed to launch in 2025. So far, nothing has gone wrong. So, other than the other mission that has had its problems, which could then end up impacting our schedule, it could, hopefully not. But if we launch on schedule, 2025, then for the exoplanet camera that I'm working on, we have been given 90 days, actually, to demonstrate that it's working. So we will have 90 days, 3 months of time to use for ourselves. There's another camera on board, too, which is actually the bulk of the mission. Ours is the most exciting, but theirs is the most. So Though that 3 months of time won't happen all at once, but it has to be completed within the first year and a half. So and then beyond that, whatever time we can have allocated, we'll keep going and keep using. And assuming everything survives and works well, we'll just keep using the camera to do more and more and more planetary systems. And then hopefully a star shade will arrive like in 2027 or 2028, and then we can do really cool things with our camera. But nominal technology demonstration is within a year and a half with 90 days of observing time.
Was there a question over here?
You may have answered this before, but your telescope will be in the night of the Earth all the time? Or
We'll be on the right. So we'll be seeing the night side of the Earth. The telescope will be seeing the night side of the Earth. It's not going to be in the shadow of. It's not going to be in eclipse, though. There will still be. The Earth. This point in space is actually fairly large, and as I was sort of mentioning, it's going to be moving around in that space, doing station keeping. And the shadow of the Earth, actually, if you look at it, it actually kind of tapers off because the sun is so big. There are parts of the sun that are visible around the Earth, even when you're directly in a line. So A, we're not going to really be in a perfect line usually, and B, even when we are, there will still be some visible parts of the sun around the Earth. It's a big star. So we're not going to be in the shadow of the Earth, but we will be. It's the night side of the Earth, the unilluminated side of the Earth, that will be visible from the perspective of the telescope.
We have a question from online. What's the other camera?
Oh, the other camera is the so-called wide field instrument, and it's actually pretty cool. It's actually pretty cool. It is so the images. Has anybody seen the deep field images from the Hubble Space Telescope? They are. It took a camera with one of its wider fields of view, pointed, which is still very small. Imagine in your mind the full moon, and within the full moon, it's always the same side facing us, so the full moon always looks the same. And there are little lunar maria on it, like dark places. The size of one of those little lunar maria is about the same size as the Hubble Deep Field of view. And that little postage stamp it's like a quarter of your thumbnail at arm's length. So that little postage stamp of field projected onto the sky, what astronomers did, and this is the so-called key project of the Hubble Space Telescope, was they took that camera and they stared at a blank patch of sky that, as far as anybody could tell, had no stars in it at all, and they stared at it for 10 days. And the image that developed from this faint, distant cosmos, what that came back was, in that little postage stamp, thousands of galaxies, like just packed. So you can imagine that whole entire sky like that, just peppered with galaxies. And then they did it in another place, in a different part of the sky, just to make sure that one wasn't weird for some reason. And it came back the same, different galaxies, but the same thing, like thousands of them in this little postage stamp. So WFIRST, the wide field image, has a field of view that in one pointing like that will be, so here's Hubble. WFIRST wide field is going to be hundreds. It's like they're calling it 100 Hubbles at once. It's got 100 times the field of view. And so it'll be able to do giant patches of sky, huge surveys of our entire galaxy. One of the most exciting projects that they're going to do is monitor the plane of our galaxy, so millions of stars at once, tens of millions, hundreds of millions of stars at once. And they're going to monitor all their brightnesses for a period of time and look for microlensing events when a planetary system passes in front of a distant light source, and the planetary system is small and invisible and you'll never see it, but it has the gravitational effect, the gravitational lensing of the planet and the star together in front of a faint light source in the background, like a star or something, will, as it passes by, temporarily amplify the brightness of that background star. So you'll be looking at this field of stars, and all of a sudden one of them will just get really bright and then disappear. And again, over here, really bright and disappear. And this is happening. And from our point of view, what we're seeing is little planetary systems passing in front of distant background stars, and because light actually bends around massive objects like planets and stars and galaxies and so on, you're just temporarily magnifying the light of the background star. And from that, you can do a survey of the whole galaxy of all the planetary systems. I mean, just like that, done. And so I have a colleague who has been studying this for years, just trying to get a census of how many planetary systems are out there and how big are the planets, what orbits are they in, all of that. And when WFIRST mission is done, he's done. There's nothing else to do after that. Like, the question will just straight up be answered, which is always nice when you can just fly one thing and the big question you wanted to go after will then just be answered and no more missions have to be flown. So he will be, or that part of the mission will be accomplishing a census, a real census of how many worlds are out there.
Question right here.
When I went to college, I was looking through the list of majors, and I didn't see extraterrestrial life and interstellar exploration on the list. Maybe you could, a few words about how you got to where you are now.
Yeah, it's actually on the list now, which it wasn't when I was in college either, but yeah, no, it wasn't when I was in college, no. I majored in astronomy and physics at UW-Madison, and then I went to University of Arizona in Tucson to get in lots of trouble with the 61-inch telescope. But while I was there, actually I was going into my senior year at UW-Madison when the movie Contact came out. And I saw that movie, and I mean, I don't know about you, but the smartest I've ever been was when I was a junior in college. I mean, I knew everything. And so I went to that movie prepared to just roll my eyes at Hollywood for trying to do a science movie. And I felt pretty confident I was going to see all the things that were wrong with that movie. And I kind of did. I mean, within the first 30 seconds of the movie, which I love. I love the opening sequence, but there's some serious errors. Anyways, by the end of the movie, in spite of all that, I was standing on my theater seat like, that's what I'm supposed to do. And I ended up, and yeah, then I get to U of A, and there's no be an alien hunter major, and there's no like, it's not just the mention of such a thing that I'm going to do that for my dissertation was like not advised. So but I couldn't let go of that. So I ended up getting in touch with Jill Tarter, who Jodie Foster spent time with at the telescope, modeling her, just trying to get the vibe of what a female scientist is like and a leader of a project, and how the culture, the SETI culture is, and with these crazy like cowboy people, doing this highly frowned upon pseudoscience. And I got in touch with her at a meeting, and I asked her in a setting like this, like she was up here and I was in the audience, and my question for her was, how could a graduate student come and work for you? And she said, that is not a good idea. She's like, we're terrible advisors. I'm never home. And also, I can't pay you. So that summer, I went to SETI. After my first year of grad school, I gave up my fellowship and went to SETI to work for $10 an hour, and just threw myself into redesigning this target list. And I knew I was an astronomer. I mean, I was a young astronomer, but I knew a lot. I did know a lot of things about stars at that point, and I could see that the target list did need to be revamped. They were looking at a lot of things that were kind of a waste of time. And we had, in ESA, the European Space Administration, had just flown a telescope that took really accurate measurements of the distances of 100,000 stars and the nearest ones. And just having that information, how far away are the stars, that completely changed our whole understanding of what those stars are like. So I took that, and out of that I applied all my own sort of judgments about what a habitable stellar system would be like, and created a whole new target list, and that ended up being like a huge chunk of my dissertation, just doing that. And then I took biomathematics classes, I took biophysics, I went to the medical school and ended up doing a PhD minor in cell biology, and persuaded NASA to let me to fund at the University of Arizona an astrobiology graduate conference, so that I could find all the other people like me around the world who were trying to do something like this and bring us all together to have our own conference as graduate students to talk about the things that we thought were interesting, because none of the big meetings, first of all, we weren't really invited, but especially not to talk about anything. And second of all, they were all regular astronomy, not astrobiology, which is what I was excited about. And we had like 75 people come, these young, new people who hadn't even gotten their PhDs yet. And darn if I'm not in touch with all those people still today. And that conference is still happening, and it has grown. And now like Japan is having their own, and the Netherlands is having their own, and like countries, these astrobiology graduate conferences are popping up. And now and universities are having alien majors now. They don't call it that, but they have astrobiology programs. It's real now. So it's almost like if you just start doing it, it'll become real. I have one final thing that I would like to share with you. This is a couple of years ago, I wrote an article for a European microbiology magazine journal, and they asked me to just write about life from the biology from the perspective of an astronomer. And it was kind of a unique opportunity, and it ended up being like the cover article with this beautiful artistic rendition of an alien Earth. And I just wanted to share with you, the whole article is available online, but it goes through a lot of the stuff that we talked about tonight. If you're interested, you can easily get it for free. Then I wanted to share with you the last couple of paragraphs, because it kind of sums up for me the situation that we're in, and this quest that we have to try to understand our place in the universe. Every aspect of the search for alien life reminds us of the Earth's smallness, the incomprehensible number of stars, the vast distances between them, the utter emptiness and bitter cold of interstellar space, the billion-year timescales over which planets are born and evolve. All of this seems to indicate our own insignificance in the grand scheme of things. But consider for one moment that there are more living organisms on Earth than there are stars in the entire universe. This unimaginable wealth of life swims in the deepest oceans, roams across the continents, flies over the highest mountains, and tenaciously inhabits the most hostile environments. Can we really ask for more than that? And yet, there is more. An event of cosmic significance is happening right now on this little dot. One species is coming into a difficult, sometimes heartbreaking, but also promising consciousness of its own ability to either maintain or destroy the world it depends upon. As a result, that species must also grapple emotionally with the paradox of being simultaneously both very small and very significant. Soon that species may realize that it inhabits a planet that is both entirely unique and yet is just one of a billion living worlds. If one tiny speck in the universe can be filled with such richness, expressing so much diversity of beauty, struggle, and adaptation, what will we discover on other worlds? As Carl Sagan once reminded us, we are a nomadic species, and our ancestors crossed continents and oceans in search of new opportunities. Our descendants may well cross interstellar space, diving deep into the arms of the Milky Way. Will they one day gaze up and strain to find the pale blue dot in their skies, marveling how perilous our infancy, how humble our beginnings, as Sagan imagined? The quest to find other worlds and the effort to understand them will transform us into the kind of species that is both capable and worthy of calling this magnificent living universe our home.
I love you.
And there's beer.
Thank you, Maggie, for sharing that. And thanks to our sponsors, Monaco Brewing Company, Monaco Public Library, Lakeland Badger Chapter of Wisconsin Alumni Association, Kemp Natural Resources Station, and Trout Lake Station, and our funding from Brittingham Fund. Next Science on Tap, November 6th, with Dave McFarland talking about wildlife research in the Northwoods.